Previously on What is COVID-19?
Now, once the threat has been eradicated, all the B and T cells that were part of this operation self-destruct to push and raise the line. Now, that is not all that scientists are working on. Hello and welcome to Rayyann Alqadry, or more specifically, a series that we call What is COVID-19, where we tell you everything that you need to know about COVID-19. Now, we ended our last episode with a complete understanding of what everyone needs to do in order to help to flatten the curve. In this episode, we're going to look at what scientists are working on with vaccines and treatments and how they actually work. There's a saying, prevention is better than cure. In medical terms, prevention is referred to as the vaccine. Yes, vaccines prevent you from getting it in the first place. They do not cure you if you already have it. To understand how they work, we need to go back to our second episode where we understood how the immune system works. Now, right at the end, once a virus is eradicated, a lot of those B and T lymphocytes, they die off. But not all of them, you see. Some stay on, some live on. Those we call memory T and memory B cells. Their job during the first fight was to record what happened. They were not in there actually fighting against the virus. They were just there to record what happened. Why do they need to record? Well, if the virus attacks again, they know how to defend themselves from it. The defense will be in a shorter period of time and will be more impactful, hence allowing you to perhaps not even get sick when the virus returns. The vaccines, they take advantage of this. They pretend to be your first fight. They take place as your first fight. Usually, vaccines consist of either dead, weakened, or even parts of a virus that the vaccine is trying to prevent you from being infected with in the first place. Now, vaccines themselves can be broken up into two main types. You've got viral vaccines and then you've got bacterial vaccines. Bacterial vaccines are what you use against a bacterial infection. Viral vaccines are what you use against a viral infection. And because COVID-19, or the SARS coronavirus number 2, is a virus, I'm going to be talking about here and after of the three different ways that viral vaccines are manufactured, or in other words, the three different types of viral vaccines. The first of which is a live attenuated vaccine. As the name suggests, live attenuated vaccines are real live viruses that are just weakened. This is done by passing the virus through an embryo, perhaps a chicken embryo, about 200 times. By the time it is done, it becomes so good at replicating in the chicken embryo, but not good at replicating in the human body. So when it actually enters the human body, it only replicates a few times, not enough for us to get sick, just enough for our immune system to be activated and to create memory T and memory B cells. Examples of diseases that have used live attenuated vaccines are smallpox and yellow fever. Both of these use live attenuated vaccines. The only thing about live attenuated vaccines is that they are live viruses, which means that someone with a weaker immune system may actually fall for the virus, for the vaccine, and become sick. This then leads us to inactivated vaccines. Inactivated vaccines are live viruses that have been killed either by using heat or a chemical like formalin. This way, the virus itself cannot cause any sickness. All it will do is that it will activate the immune response. What this means is that anyone with even a weaker immune system is able to use an inactivated vaccine. Now, diseases that have used inactivated vaccines are polio and rabies. Now, the only thing about inactivated vaccines is that because they are dead, because they are not real live vaccines, their immunity does not last as long as live attenuated vaccines. So you may need some booster shots to make sure that it goes your entire lifetime. Now, besides live attenuated vaccines and inactivated vaccines, there are subunit vaccines. Now, just like inactivated vaccines, subunit vaccines are somewhat weaker than live attenuated vaccines and may require you to take booster shots. But at the same time, they can be used for people who have weakened immune systems. Now, what subunit vaccines do is that you take any single part of a virus, whether it's the DNA or the sugars around the membrane or the capsid that is made of, or some proteins in there, and these are what are used as the vaccine itself. So these vaccines are targeted to specific parts of the virus. Now, there are many different types of subunit vaccines, and they all depend on what part of the virus you're using, whether it's the gene or the sugars around it. Now, examples of diseases that have used subunit vaccines are things like the whooping cough and shingles. Both of these use subunit vaccines. Now, that then covers all three different types of vaccines. So we've got live attenuated vaccines, which are just weakened viruses. You've got inactivated vaccines, which are dead viruses. And then you've got your subunit vaccines, which are just parts of a virus. Now, with the powers of this magical medicine that is the vaccine, comes the immense amount of time required to make one. Time that sadly not many have. Now, so meanwhile, researchers are looking at pre-existing drugs and other ways that we could perhaps be able to treat COVID-19. Announced by the World Health Organization on the 18th of March of 2020 and joined by over 100 countries by the 21st, is an international clinical trial that the WHO has called the Solidarity Clinical Trial. Its aim is to identify whether any of 4 different treatments can be used against COVID-19. These treatments are to be administered in addition to the local standard of care to anyone above the age of 18 who has been hospitalized with COVID-19. And with that out of the way, we can look into what these treatments are. The first of which has to do with a single drug, and that drug is called Remdesivir. Remdesivir was originally made to be used as an Ebola drug, and it had some partial success in fighting against Ebola, but was eventually superseded by monoclonal antibody treatments. Now, how it works seems to perhaps be effective and could be used in fighting against COVID-19 or the SARS coronavirus number 2. What it does is that it stops the virus from replicating in the first place. It goes to an enzyme that we call a polymerase. This polymerase is like the worker that will break apart the RNA and put it back into the duplicated version of the virus. Now, when the polymerase picks up Remdesivir, it thinks that Remdesivir is one of the parts that we call adenosine or adenosine. When it puts this Remdesivir in, thinking that it's adenosine, the Remdesivir will eventually destroy the entire RNA to the point that the RNA can't be used and the virus stops replicating. This principle seems to have worked, especially even in cases of coronaviruses. When tried with SARS and MERS, it worked to a certain success with animal trials. In fact, a paper published in Nature in earlier February of 2020 showed that Remdesivir seems to be able to work, but only in lab environments. So there weren't any full-scale tests that were done on humans in a proper controlled clinical trial yet at that time, which is why the WHO chose to put Remdesivir in this list. Now, the second treatment, it's actually 2 different drugs that are being tested. What are those 2 drugs? Before you continue, the drugs that I'm about to mention are hydroxychloroquine and chloroquine. The reason I have this break is because this video was originally scheduled to be recorded on the 20th of May, and that was the recording day. However, 2 days later, a paper was published in The Lancet that showed that certain trials with hydroxychloroquine and chloroquine proved to have an increase in mortality rates. Now, I was able to fit that piece of information into an updated version of the video. However, 2 days ago, today is the 27th of May, very recently, the WHO paused. They had a temporary break on the hydroxychloroquine and chloroquine arm of the Solidarity trial, which meant that trials with hydroxychloroquine had been paused for a moment. Now back with the video. Chloroquine and hydroxychloroquine. Hydroxychloroquine and chloroquine were originally made as malarial drugs, anti-malarial drugs, which means that they fight against malaria. Now, malaria is caused by a parasite that we call Plasmodium. Plasmodium lies in the red blood cells, and this hydroxychloroquine and chloroquine are capable of entering the red blood cells. Their drugs are attracted to any positively charged particles that we call protons. These particles are also what makes things acidic. Now, when they're attracted to these acidic locations, they reduce and neutralize the acidity in that area by collecting up all the protons. When it does this, that area becomes less acidic. One of these areas are these stomach-like compartments in Plasmodium that handles the breaking down of poisonous material. So it goes there, reduces the acidity, and the Plasmodium is not able to break down poisonous materials, making it more prone to those poisonous materials. Now, this could also be helpful for stopping cytokine storms, which you talked about in the second episode. Cytokine storm, in the first place, they start when an immune cell thinks that one of the human body cells is a threat. For it to think that in the first place, it needs to have attacked one of the human cells, and when it attacks it, it breaks it down. That breaking down is done in a part of the immune cell that is called the lysosome. The lysosome will break it down, and then those parts will be displayed around it to tell the other immune cells that this is the person we're trying to fight. Now, hydroxychloroquine and chloroquine reduce the acidity in those lysosomes, making them not able to break down the human body cell. Now, there have been certain trials, very basic trials done in China and France that showed certain success in hydroxychloroquine and chloroquine, but a very recent study published in The Lancet showed that some of these cases, when they tried using hydroxychloroquine and chloroquine actually increased the mortality rate. Now, the third treatment as part of WHO's Solidarity clinical trial is a combination of two drugs, Lupinavir and Ritonavir. Lupinavir and Ritonavir are both used together to fight against HIV, or more specifically, they are HIV protease inhibitors, which means they stop a specific enzyme in the HIV virus called a protease. This then stops it from replicating. Now, this is mostly the work of the Lupinavir, but when Lupinavir is left alone, it is consumed too quickly by our enzymes before it can have any effect, which is where the Ritonavir comes in to stop that from happening. Now, both of them together have shown certain success in some small clinical trials. For example, a study in Wuhan with about 200 patients showed that mortality rate seemed to be affected by Lupinavir and Ritonavir, but in a positive way, in the sense that it brings down the mortality rate. Now, the fourth treatment in this Solidarity trial has to do with Lupinavir and Ritonavir, but plus one extra thing. The fourth and final treatment as part of the WHO's Solidarity clinical trial is a combination of Lupinavir, Ritonavir, and interferon beta. Interferon beta is actually a cytokine. One of those cytokines is employed during an immune response. Now, certain studies have shown that interferon beta itself, left alone, is capable of treating mice that had MERS. It has also been shown to have some success in SARS. However, when put together with Lupinavir and Ritonavir, a study in early of 2020 showed that It wasn't that successful in MERS, in treating MERS in mice. However, MERS and COVID-19 are rather different, and that difference could be a major part in the success, in the possible success of this treatment. Now that then covers all the different treatments as part of the Solidarity clinical trial. But that is not all that scientists are working on. Scientists are also looking at stem cell and plasma treatments. Both of these are other ways that we can hope to be able to treat COVID-19. This brings us to the end of this episode. Thank you for watching. I hope it was educational. And remember, stay safe, learn more, and we will get through this. Goodbye.